So thanks, Addie, for that very good observational and experimental introduction. I'm going to talk a little bit about modeling, and again, this is work that we're doing with Dan Britt's class center as part of the Survey Institute. Remember, the A in class stands for asteroids, so I'll be talking about the moon and asteroid surfaces. The dynamics are similar. The main difference really is just the G level. So at small asteroids, it's, for all intents and purposes, 0, where you have a fairly modest but not negligible value of G on the lunar surface. This is just another representation of the data that Addie showed of this lofted dust. So there's this, it just was referred to in the last question from Pamela in the discussion there. There's sort of two kinds of lofted dust that we talk about. There is the low altitude dust that I'll refer to as hopping dust, and then there's dust that is actually streaming away from the surface. In this example here, and this is a sort of an oddly photoshopped image of some of those surveyor things that took me a long time to figure out what was really going on. But what you're looking at here is probably very, very low altitude dust, maybe a meter or so above the surface. And just to touch on the question about Itokawa, the reason that we've got these interesting observations here from the moon, where we can see this so-called lunar horizon glow, is because that surveyor landed in a crater and was therefore able to look at the horizon with the sun below the horizon, but illuminating the, you have basically a ridge on the horizon that you can see dust just barely above the surface. If you're on a perfectly smooth surface, it would have been much harder to get that sort of an observation. And you have to be able to be pointing your camera very, very close to the sun direction. And those of you who've worked on spacecraft missions know that the camera engineers are not too happy with pointing the camera close to the sun. So it's unusual to get these very, very high phase angle eclipse observations. I'm going to just say one more thing about observations, and then I'll move into some of the numerical modeling. And this is an image taken by Surveyor 3 after it landed on the surface of the moon. And so what I want you to notice is this little waffle pattern in the surface of the lunar regolith. And this is just the texture on the foot of the Surveyor lander. It hit and bounced. So it hit and bounced over, and it left this impression in the lunar regolith. And then I had the date up there. About 2 years later, the Apollo 12 astronauts landed near Surveyor 3, a couple hundred meters away, and walked over to it and brought samples back and took a lot of pictures. And here is what that footprint looks like. They had better cameras, so you get a nicer view. The point here is just, it hasn't changed. Okay, so here's this very fine dusty surface. The thing lands. We've got a before and an after picture that's 2 years apart. So it's just to remind everybody, because we're talking about this fine dust dynamics and dust hopping around and going all over the place, and it's easy to let our imaginations get carried away with an idea of this sort of roiling atmosphere of dust. Most of the time, and in most locations, it's quiet. It's quiescent. We don't have a lot of dust moving around. So one of the seminal works on the sort of the initial Galilee in 1996 is looking at asteroids and said, okay, if we take, as Addie described, you put an object in the solar wind, on the day side, it is hit by solar UV, so it emits photoelectrons, so you get a net positive charge, and you have a photoelectron sheath above the surface, so you have an electric field that's pointing upwards. If I've got a positively charged particle near that surface, so if I take a dust particle, I lift it off the surface, I hold it up in the solar UV, it emits photoelectrons as well, so it's got a positive charge. The asteroid surface beneath it has a positive charge. They repel each other. So that dust particle gets pushed away. This force is obviously very weak, but if you're near an object that's got a very weak gravity, it will move away. So Lee's work said, let's just calculate what is the size of a levitatable particle as a function of the size of the asteroid, which is just determining the strength of the gravity. If you have a small object, it's got a weak gravity. It should therefore be easier to lift larger and larger particles off the surface and have them reach escape velocity from that surface. So here's another picture of Itokawa. Addie showed a picture of this in the previous talk, and I particularly like this image that Dan Durda provided to me. This is also a photoshopped image, but it's to scale, and it's just to give us a little bit of something that we can relate to. Here's a car and a sunbather. To scale with an image from the surface of Itokawa, and you see lots of boulders, macro-regolith, and you don't see a lot of micro-regolith, which is consistent with this sort of zeroth order story that an object with weak gravity doesn't have a lot of dust on it. Now, if we move to a slightly larger asteroid, this is Eros, and Addie mentioned these, showed an image with these ponds, these very smooth, flat surfaces that were discovered on Eros by the Mir Shoemaker spacecraft. And this provided a really good new observational test of the whole dust dynamics problem. So it was our first really good new observational data from that lunar data that Addie reviewed. We've got this distribution of a couple of hundred smooth deposits of apparently dust on the crater floors in asteroids. How are they getting there? Well, we've done a couple of models of those where we're just numerically integrate the trajectories of particles. So we have a photoelectron sheath, as Addie described, on the day side. We calculate the surface potential, we calculate the charging currents, including the solar wind, including photoelectron emission from the particles, and say, okay, if a particle gets knocked off the surface somehow or other, it could be electrostatic separation, it could be from some thermal quake that introduces some vibrations, it could be an impact, it could be a secondary impact. If we knock the particle off the surface, then what happens to the motion of that particle? So here's all the gory details of the various charging currents, and then the equation of motion. So put that in, the computer knows how to handle this stuff, and we can take a look at what happens. We do use a couple of different models for what's the electric field above the surface. So there's simple theoretical approaches, and these have been validated by particle and cell simulations. This plot is just showing the density of the photoelectrons above the surface of any body in the solar wind and the solar UV flux. What's the force balance look like? So if we take a look then at the moon, we've got, as a function of height above the surface, here on the horizontal axis, we have, for different size particles, the ratio of the electric field upward to the gravitational force down, and where those equal 1 is where you would have a particle exactly balanced, and you can see that the electric force is much greater than the gravitational force for some of these particles if you're well above the surface, but when you're close to the surface, let's see, I said this the wrong way. Negative means G is down, E is up, and these are where your particles are feeling a net upward force, and then when they get up above the photoelectron sheath, then they fall back down. Because this crosses 0 and changes sign, your particles can undergo an oscillating motion. So we'll show that in just a second. There is, I'll just go back 1 second, where these curves cross 1 is where you've got a possibility for stable levitation. And so there are two levitation heights. The upper one is stable and the lower one is unstable, and on the horizontal axis in this plot is the particle size. This is for the moon. So this is going from 1 micron down here up to a couple tens of microns, and the stable upper levitation height is actually quite high, hundreds of meters. That dust in the surveyor image that Addie showed, and then I showed an image at the beginning, this thin line of dust above the horizon is only, based on analysis of that image, only about a meter above the surface. That dust is not floating. It is not possible for dust particles to be stably levitated at a meter above the lunar surface. The stable levitation height is much higher. So what does that tell us? That tells us that those particles are actually hopping. They're not sitting up there floating. You're getting particles that are going up and down. They spend more time at the apex of their trajectory, and you're seeing this thin cloud just above the surface. So what do some of these trajectories look like? Here's an example. This is now going up to about 20, 30 meters in height, and I've got two curves labeled here, a red curve at 0.21 microns and a blue curve at 0.22, then a third one, a black one, is a ballistic trajectory. And you can't see the blue or the black because they're buried down here in this little tiny bit in the lower left-hand corner. So if we zoom in on that, in this green spot on the next slide will be what's in that green spot. So here now we can see those three different trajectories. And this is to illustrate how sensitive the dynamics are to the particle size. So the 0.21 micron particle is the one that ended up going to a high altitude. A slightly larger particle has just enough more inertia that the electric field is not able to get it up above the sheath, and it just ends up following a slightly modified ballistic trajectory and falling. If we ignore the charging forces entirely, then the particle follows this black curve. So it's a very, very sensitive function of the particle size. Here are some more examples. So we've got here a particle that's going through this typical oscillatory motion that you can see the particle gets accelerated above the surface by the electric field in the photoelectron sheath. Once it gets high enough, it's out of that photoelectron sheath, the electric force drops away, it starts to fall back towards the surface. It still has a positive charge because it's emitting photoelectrons from solar UV. So once it gets closer to the surface, it feels, and it enters back into the photoelectron sheath, it feels that electric force push it back up, and you get this oscillating motion. So you can get this stable levitation, but at these higher heights, and that's a function of the particle size. We're going to zoom in again on the lower corner here, and just to show you some of the various complicated trajectories that you can get depending on the particle size, what the photoelectron current is, and a lot of these properties that are not well understood. So, what do these simulations from the moon mean? They tell us that the surveyor horizon glow particles are not floating, but are on ballistic trajectories, or perhaps slightly modified ballistic trajectories. So the electric force is responsible for separating those particles from the surface and causing them to hop, but they're not going through this floating trajectory that is seen. The height of the horizon glow is on the order of a meter, and that constrains the launch velocity of those particles to be about a meter per second. Now, we also simulated what happens if you're on a complicated surface, and we looked at this with the Eros dust ponds. So suppose you've got shadowing. So shadowing affects the photo emission and therefore the charge distribution on the surface. And we found that you can get net deposition of dust particles into craters. So this gets to your question about horizontal transport. Our three-dimensional modeling of dust transport on Eros, together with the distribution of where those cons are on Eros. They're preferentially concentrated on the equator because of Eros's obliquity. has a very special orientation with the seasonal photoelectron sheath. We found that that's consistent with dust transport there. I'm out of time, so I'm going to jump ahead to experiments that show these things really happen, but then our open questions, which will tie into measurements that we want to make, and some experiments that Addie will be doing in the lab as well. What are the surface potentials on asteroids and moons as a function of time and location? What are the near-surface plasma properties and electric fields like? A lot of the things that go into these models are our best guesstimates on what those properties are, and what are the conditions that lead to launching of the particles off the moon and asteroid surfaces. We really need better data to understand what's going on with that dynamics. I'll stop there.